What if we told you that there are regions in the universe where time and space warp to such an extent that they swallow everything that comes near them, even light? Welcome to the enigmatic world of black holes, a concept that has puzzled, intrigued, and inspired generations of astronomers, physicists, and science enthusiasts alike. Black holes. These two words conjure up images of a mysterious, insatiable cosmic entity that devours everything in its path. But what exactly is a black hole? In simple terms, it is a region of space where gravity is so strong that nothing, not even particles or electromagnetic radiation like light, can escape from it. But don't let the simplicity of this definition fool you. The concept of black holes is one of the most complex and intriguing in the entire realm of astrophysics. The idea of black holes wasn't always part of our cosmic understanding. The first theoretical suggestion came from an English natural philosopher and cleric, John Michell, in the year 1783. He proposed the existence of what he termed dark stars, celestial bodies so massive and dense that their gravitational pull could prevent even light from escaping. This was a radical idea, one that challenged conventional thinking and opened up a whole new world of possibilities. Fast forward to 1915, a certain Albert Einstein reshaped our understanding of gravity with his general theory of relativity. This theory, a monumental leap in the realm of physics, replaced the Newtonian idea of gravity as a force and instead presented it as the curvature of spacetime caused by mass and energy. Now, what do we mean by spacetime? Well, think of it as a four-dimensional fabric that makes up our universe. Imagine a trampoline. If you place a heavy ball in the center, it will create a dip or a curvature. This simulates how a massive object, like a star or a planet, distorts the fabric of spacetime around it. The more massive the object, the greater the distortion, and hence, the stronger the gravitational pull. Einstein's theory also proposed something quite extraordinary. It predicted that if an object is dense enough, it could curve spacetime so drastically that it forms a bottomless pit, a point of no return. This, my friends, is what we now call a black hole. But what makes black holes so fascinating is not just their existence, but the profound effect they have on their surroundings. Black holes are celestial vacuum cleaners, pulling in everything that ventures too close, even light itself. This is where the term black comes from. Their gravitational pull is so intense that not a single ray of light can escape, rendering them invisible to the naked eye. However, it's important to note that black holes aren't just destructive forces. They play a crucial role in the universe, influencing the formation and evolution of galaxies. They even have the power to bend time itself, slowing it down near their event horizon, the boundary marking their point of no return. But it was not until decades later that we would get the first real evidence of these cosmic monsters. Despite their invisibility, scientists have devised clever ways to detect these intriguing entities, turning what was once theoretical into the tangible. But more on that in the next scene. The year is 1971, and astronomers are observing something strange in the constellation Cygnus. Imagine a time when black holes were just a theoretical concept, a mathematical anomaly that seemed too bizarre to be real. But then, a strange discovery in the constellation Cygnus began to change everything. This celestial mystery was named Cygnus X1, an X-ray source in the sky that puzzled scientists around the world. Cygnus X1 is not an ordinary star. It's a binary system, a cosmic dance between two celestial bodies. One of these bodies is a blue supergiant star visible to the naked eye. The other, however, is unseen, revealing itself only through its gravitational pull on its stellar partner and the high-energy X-rays it emits. Astronomers began to suspect that this invisible partner was a black hole. But how could they be sure? The answer lies in the nature of black holes themselves. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. This makes them invisible to our eyes and telescopes. However, they can be detected indirectly. As matter from the blue supergiant star is pulled towards the black hole, it forms an accretion disk. This disk heats up to extreme temperatures, emitting X-rays that we can detect here on Earth. The characteristics of these X-rays, along with the star's motion, suggested the presence of a black hole. This was the first time that astronomers had compelling evidence for the existence of black holes. Cygnus X1 became a touchstone in astrophysics, heralding a new era of black hole discovery and research. It transformed black holes from mere theoretical curiosities to tangible, observable phenomena. Cygnus X1 was the first, but it certainly wasn't the last. This discovery opened the door to many more, each one adding a piece to the puzzle of our universe and bringing us one step closer to understanding the enigma that is a black hole. Imagine being able to see the unseeable. That's precisely what happened in 2019. In a remarkable feat of scientific achievement, we managed to capture an image that was previously thought to be impossible to obtain. The first ever image of a black hole's event horizon. This was not the work of a single telescope, but a network of observatories across the globe, collectively known as the Event Horizon Telescope, or EHT. You might wonder, why is this image so significant? Well, this image is like a snapshot of the edge of existence. Everything that crosses this boundary, the event horizon, is consumed by the black hole, never to return. It's a one-way trip into the unknown, a place where our understanding of physics breaks down. But capturing this image was no simple task. Black holes are notoriously elusive, and their event horizons are even more so. They don't emit light or radiation that we can detect with our traditional telescopes. Instead, the EHT relied on a global network of radio antennas, effectively creating a planet-sized observatory. This image, a blurry orange ring surrounding a dark abyss, was the first direct visual evidence of a supermassive black hole and its shadow. It validated predictions from Einstein's century-old theory of general relativity. The ring of light we see is heated matter swirling around the black hole just before it plunges into the event horizon. Not only did this image confirm the existence of black holes, but it also provided a means to study them directly. It opened a new window into the study of black holes, their environments, and the laws of physics under extreme conditions. This image was more than just a picture. It's a testament to the power of collaboration, the advancement of technology, and the relentless curiosity of the human spirit. It's a symbol of what we can achieve when we dare to look beyond what we can see, when we strive to uncover the mysteries of our universe. This image was a testament to human ingenuity and our never-ending quest for knowledge. So, what do we know about black holes today? We've journeyed from the birth of the black hole theory through the indirect proof and finally, visual proof. Now, we stand on the precipice of the present with the most recent discoveries and theories in hand. In the last few decades, our understanding of these cosmic phenomena has expanded exponentially. The development of radio telescope technology has allowed us to detect and study black holes that were previously hidden from our gaze. We've found that these celestial monsters are not just solitary hunters but often reside at the heart of galaxies, including our very own Milky Way. Moreover, we've begun to unravel the mystery of what happens inside a black hole. We used to believe that anything unfortunate enough to be drawn into a black hole was doomed to be crushed into a singularity, a point of infinite density. However, some scientists now propose that black holes could in fact be portals to other universes. This theory, while still controversial, has opened up a whole new realm of possibilities for our understanding of the cosmos. The discovery of gravitational waves has also provided a new way to study black holes. These ripples in the fabric of spacetime, first predicted by Albert Einstein, are caused by the collision of massive objects like black holes. By studying these waves, we can gain insights into the violent events that create black holes and the way they interact with the universe around them. And yet, black holes continue to baffle us. Despite our advancements, there are still many questions left unanswered. What happens to the information about the matter that falls into a black hole? Can we truly understand the singularity at the center of a black hole? While we have come a long way in understanding these cosmic beasts, they continue to hold many secrets, challenging us to push the boundaries of our knowledge.